Hello! Hello, everyone. Welcome to stream. I hope you enjoyed that stunning MIDI of Undefeatable from the Sonic Frontiers soundtrack. I have exciting news today. I managed to get one of those leap motion hand trackers on eBay. So now I can, like, wave and stuff. Hi! It's still not great hand tracking. I definitely should be mounting it in a different place than I am. But, you know, it does basic stuff. Alright, so yeah, as I mentioned in the stream title and on Mastodon and Discord before, this was supposed to happen on, what was it, Wednesday? But I had just not had that much sleep that night, and, well, you don't want to do engineering on a low amount of sleep. That's not how you get working circuits. You can make circuits when you're low on sleep, but you can't make working ones. So yeah, tonight I've gotten a good amount of sleep, and I'm well rested and ready to get going. Hopefully our connection holds out. Our Thursday stream that we normally do had to cancel because our connection was not very well made. It's like, you know, you spend all the time laying like 14 billion kilometers of superluminal transit network, and then the last like 3 miles of cable on Earth, they just can't get you that bandwidth. So hopefully it holds out. So yeah, let me take us here. Go to the corner. Alright, chat, this is my desktop. I hope you're excited. I've removed all the icons from it so you can't see anything. We have Bava here. I don't know how many of you guys know Bava. Bava's great. And so Bava's just gonna hang out on our screen. We can pet Baba with the mouse. Right, and yeah, so I don't want to do this in silence, so I got a subscription to Monster Cat so we can have some background music. Let me add that real quick. Application audio capture. Alright, and I'm gonna start this turned down a little bit because I don't have this set up as my standard audio capture. Wait, you know what? I should actually, if we set this up to capture this window, then it should automatically, like, turn the volume down when I speak. So here's hoping. Yeah, this is just Monster Cat's chill playlist. We'll see if it's any good. We've got a pretty good amount of music in here. See how long it holds out. Oh, there's 111 pages of this. Okay, never mind. We should be fine. And is disabled. Well, okay, I guess that's just fine. We can turn this up a little bit. And yeah, so when I'm talking, those audio levels should automatically go down so you can hear me clearly enough. So, alright. Let's just get going here. So, here's our main goal. Oh, I know him, he's you. I don't know what you mean by this, Pancake. Oh, Baba. Yes, that's true. Baba is you. So, what we're trying to do here, right? Wait, I should turn this down a little bit on my end so I can... There we go. Right, so what we want is a USB hardware device where you can upload or otherwise send audio files and assign them to buttons. Oh, a USB hardware device with buttons. That's important. It should have buttons and like probably some feedback LEDs as well. Let's see. They should be able to upload audio files and assign them to buttons. When a button is pressed, play that audio. It should show up to the host computer as a USB audio input. So that's the sort of overview. So we want to have some buttons and feedback LEDs for interactivity. I was thinking I have some of these tiny little LCD displays that are like, they're like maybe like a centimeter high and like 3 centimeters long. And I have like a couple of those, and we could use those for buttons or something. Like each button has one of those LCDs to give some more information about what's on it, if that makes sense. And let's see. So yeah, so some questions we have right now. We want to say, what microcontroller? What microcontroller should we use? And if we're using a microcontroller, here, let me put this. It's possible we'll want to use multiple. If we're using a microcontroller that doesn't have USB capabilities built in, we want to know how to bridge that connection, basically. I propose the following question, Don't worry, Pancake, I'll explain everything as well as I can. So let's see. So if it's not USB capable, we'll probably need like a separate chip to make that connection, you know? And then like have it send audio. If we use an ESP32, we have the capability of doing a web interface. Like I've done this before. With an ESP32, you can basically like build a little web page. Even like, you know, you could even like use a web front-end framework like React or something, and just put together a web page that when you pack it all up, it lives on the microcontroller, and the microcontroller can serve that web page, and then like run the API on the back end. So basically it has its own like web interface. If we have a microcontroller that's USB capable on its own, we could have like a separate we would have to build like a desktop app for it, or like maybe we could like make it show up as a USB drive or something. So that's kind of what I'm thinking. And of course, anyone in chat, feel free to chime in at any point. I am happy for any suggestions or questions you might have, and I am happy to explain stuff. So just ask in chat if you got any questions at all. I promise I don't bite. Mostly. Alright, so I suppose the first step is we want to look at microcontrollers. So, options we have for that. So, a couple of things I've looked into already before this stream. There is this component, the CP2615, which, if I pull up the data sheet here, I should just open this in. So this is a, it says it's not recommended for new designs. Unfortunately, there's not like a, more up-to-date version of this part. Like, they're not making another version, but this part's still supported up to 2026, so we can absolutely use it for this project if we want to. So basically, this thing is a USB audio to I2S audio bridge. What this means is that it will show up if you like connect it properly to a USB port or something. It will show up as a USB audio device, like with a USB input and a USB output. And then all of the data from that, like when you put data into it and when you take data out of it, that goes through I2S, which is a sort of standard audio protocol. So, let me move this over here, actually, so my VTuber model isn't getting in the way. Alright, so yeah, basically you plug this thing into your computer and it shows up as a USB device, and it takes in sounds. Like, it can record audio, well, recording audio, like when this thing shows up as a microphone, that means, basically whatever it's connected to on the circuit board is sending it audio data based on, like, I2S. And when it shows up as like a speaker, like an audio output, that means that like any audio you play to it will go out to the connected device also over I2S. So it's sort of like it's like a bridge between your computer and like a USB protocol and the microcontroller, which is usually using a much simpler protocol. So yeah, this is a possibility I'm thinking of. So that is the one there. One other neat thing about this particular chip, let me find it. Yeah, here. So this chip also has like a protocol for allowing a user application to control like some of the I/O pins on this device. So like you could have even like non-audio direct communication between your computer and the microcontroller on the board. So like this is something I've looked into as definitely I'd say this is definitely a possibility. If we're using an ESP32 and doing like the web interface thing, then I would say like it's definitely a very good thing to potentially do. But if we already have a USB capable DSP chip, then we don't have to use this or worry about it. And it is like $10 if you're buying it in low quantities, so you know, you don't want to make it too expensive. So we'll keep that here for now. I wanted to look into some other DSP microcontrollers that we could maybe use directly instead of having to worry about an interface chip to bridge the connection. So the first step is usually just a Google search. I'd say, you know, depending on what you're looking for, often DigiKey's another good place to look. So this is a website just for ordering random, like, individual electronic components. So they've got, like, all sorts of stuff. So if I just search USB DSP microcontroller. DSP stands for digital signal processing, by the way. So, like, DSP in microcontroller terms is a microcontroller that's been optimized for doing the sort of math calculations that you would need to do when you're processing audio. So, let's take a look at some of the options we got here on DigiKey. So, this is a microchip microcontroller. Oh, DSP can program them themselves. Well, that's usually going to be useful for like big production runs. We don't need that. Let's take a look. So, 16-bit, 256K flash. Not too expensive. Again, this isn't like, you know, we're not like building a product with this part. Listen chat, the last thing I want to do is commerce here. That's not anything I want to get involved in. You guys can do that yourselves. So that being said, we're not going to be like buying 100 of these things. So if we're just buying a couple, you know, $10 isn't too bad. Let's see. So what kind of capabilities does this have? PICs can be irritating, like just as a microcontroller platform. I've used them in the past, and they have some features that I just kind of like, like I could do without them. Which means that this microcontroller is already like sort of inherently down in my listings for being a PIC. 3.3 volt operating voltage. Wait, does this thing... Oh, this thing doesn't have a USB interface, does it? Oh no, it does have it. USB 2.0 full speed interface. Not my first pick, as it was. Okay, let's see. Let me just take a look at this section on the USB. Now chat, when you're looking at electronics, the first thing you need to know is when you're going through the datasheet, don't get intimidated when it says it's 600 pages long. You don't need to read all 600 of them. You just have to sort of know where to look. So let's see. USB on the go. Wow. Finally, USB that can fit into my fast-paced, busy lifestyle. Oh boy, okay, yeah, sure. What is USB on the go? What does that mean? What differentiates USB on the go from regular USB? Use USB devices such as tablets or smartphones to also act as a host. So I guess that just means that this thing can act as a host, huh? This is so bus logo to me. That's extremely reasonable. USB on the go! Hey chat, you're not satisfied with standard static USB? Well now you can have a solution that goes where you go, with USB on the go. Huh, neat. Now, I will say the programming is probably going to be a bit more complicated if we're using a microcontroller with USB support. Just because, like, I've never actually done USB programming before, so I'll have to look into that and figure out how to do it. Let's see. And use of the USB specifications and other third-party specifications or technology may require a license from various entities, including but not limited to USB Implementers Forum Incorporated. You guys really make some choices, huh? I guess I'll have to look into that. Many useful resources related to USB on the go are provided on the main product page of the Microchip website. I guess this is entirely in a separate datasheet. Let's take a look. Oh, oh, it's a dead link, chat. This Monster Cat song is one of the woobliest songs I've ever heard. Listen, it's chill. That's what it says on the playlist, at least. Wait, are you just playing the same song over and over again? I didn't even notice. Okay. So we're not playing the same song over and over again anymore. Oh, this one has vocals? Is there a way to filter it to ones that don't have vocals? Because I don't... Let's just skip. Okay. Well, I guess I'll have to manually skip when we come across one that has vocals. Okay, well... Okay, maybe most of them have vocals. I was looking for some trouble, you were looking alright. Progressive house moment. Guess I gotta like go through and make my own playlist. Songs that don't have people singing in them. I can hear a human making noises there. There's a lot of humans making noises that might be words, but it doesn't seem like it's like singing. We'll see if that continues. This is the house music liberals want. So true, Pancake. Oh, I don't have the chat. I don't have chat on screen in this one. Let me fix that real quick. Give me just one sec. Go in here. Add a stream chat. thought it was like a tape effect, but both of these songs have been warbling in pitch and speed a lot. Well, that's strange. I'm not doing that on my end. Hold on one sec, hold on one sec. Here, what I can do is I can listen back on my stream. Let me see. Oh, the infinite loop. Okay, hold on. The infinite loop. Okay. I wonder how do I mute this just on my end, but keeping going to the stream? How do I mute this just on my end, but keeping going to the stream? Okay, if I mute it, I can hear it for a second. Okay, if I mute it, I can hear it for a second. Okay, if I mute it, I can hear it for a second. Oh wait, it'll just keep going through the stream. Oh wait, it'll just keep. Okay, we just gotta keep going. Okay, yeah, I don't know why that's happening, Pancake. That's weird. Yeah, I don't know, it's doing like some... Are you sure your audio cable's in all the way? Okay, anyway, let's get back to the stream. Do let me know in chat if this is happening to multiple people, but I think it's probably fine. Okay, so we have to look up this. Are you going to copy properly? Let's see. Let's see what we got here. This doesn't seem like it's saying anything useful here. Yeah, no. What are you on about? Section 11. Maybe I was looking at the wrong manual. Oh, this is just one section of it? Huh. Can I just get the whole thing, or do I have to look it up one section at a time? I guess I can Google section 11. Here. Let me see if Microchip has like a web page for this thing. These appear to just be... I need the full text, Microchip. When you're calling out. Oh. So many of these have voice on them. This is also just section 1. I need the whole thing, Microchip. What? This DS Pick 33 EP. DS Pick 33 EP. Hey, let me look at the actual product ID. ESPAC 33. So pick 33, EP 256, MU. So this is the MU family. Okay, USB connectivity. Is this gonna be it? Oh, I just need a manual for the chip. What do you mean explore MP Lab Discover? I don't need to use your silly application. You see, this is not helping my opinion of Microchip's product family, is that they've done this to their documentation. Okay, is this going to be the... Hey, we found it! USB on the go. All right, chat. Let's see. USB full speed support for host and device. Confirm the audio problem is on my end. Okay, gotcha. So I'm glad that's not like a stream issue. Okay. Implementation advice. This really isn't that much more helpful, if I'm being honest. Do we have, like... Oh, okay, it's just they put the registers, like, in section 2. Weird. Okay, a brief overview of USB operation. That's true. For identifying all devices connected to it, initiating all transfers. Okay. We're not going to be using host mode anyway. Alright. And ideally, we're just going to use the USB bus for power. Like, we could theoretically have a separate power supply for it, but that's the whole, that will be a whole thing. Oh, I was gonna make an overlay to put chat on stream, and I just got totally distracted by the audio thing. Let me fix this. That's strange that the manual is split up like that. Yeah, manuals are indeed hard enough to read as is. Welcome back, Wimbry. Okay, this to that color. Can we get like a outline? Yes, we can. Oh, there we go. Listen, it's fine. It happens to all of us. Okay, and then we have this overlay as... Put that up there, so it's sort of above me. And we put this up here as a browser source. And put something in chat. There we go. Hopefully that's big enough to see clearly. I can probably make it a little bit bigger. Just make the text shadow there. Could make it a little bit bigger than that. Okay, there we go. Okay, now we have chat on screen. I can move it up a little bit so it doesn't get caught on my horns. Perfect. All right. This is just describing how the USB protocol works. I'm more interested in finding out the process for doing it on this microcontroller. And we have to set that up. All USB endpoints are implemented as buffers in RAM. The CPU and USB module have access to the buffers. The semaphore flag system in use. Endpoint can send and transmit at the same time. Buffers can be located anywhere in RAM. Each endpoint is controlled by an endpoint control register, U1 EPN, transfer direction, handshake, and stalling properties of the endpoint. Alright, so buffers are shared between the CPU and USB module. It doesn't seem like it's going to be too bad to implement. So, like, we'll put this down as an option. Okay, let's... Let me know if the words in this song get in the way or become distracting. Manuals in far too many places. Take it from someone who has this specific auditory processing issue, it's a-okay. ESP32 is a happy little chip, much processing power, low cost. I'm glad it's okay. I'm glad the audio levels are okay. Let me know if that changes, and I can absolutely skip songs if people don't like them. Yeah, I've done projects on the ESP32 before. It's a very good microcontroller. A very handy little guy. The big issue with an ESP32 here is that I don't think it has native USB support. This guy wishes he was faster than people. Darn Pancake, absolutely destroying these Earthlings. Let me copy this unreasonably long product name. Manuals are in far too many places, but the USB implementation doesn't look too bad. It would cost $9.35. Pancake, you gotta stop roasting the Earthlings. Gotta be friendly. I don't know where this energy is coming from, I'm sorry. No worries, Pancake, no worries. Should mention that it's $8.55 at 25, but that is far too much for me to be spending on this project. It'll be what? We got my trusty TI-84 plus CE. Not sponsored, not sponsored. $213 just on microcontrollers? Yeah, no thank you. I don't know. If this microcontroller was like really good, then I might consider buying that many to have a stockpile for future projects. But like, that's only if it's really good, you know? And I am not inclined to believe that a PIC is really good. Okay, this is just another case of the same microcontroller. Ideally we wouldn't be using a QFN. Like, I theoretically could get it done. I mean, okay, so it depends on if, so I'm planning on ordering these off of, the PCBs off of JLC. Like, if they have these and they're like PCBA supplies so that we could get them to solder them onto the board, then that's fine. But like, I don't want anything that's too complicated to solder because I don't have a heat gun at the moment. And like, I have access to a soldering oven. But like, you know, it's like, kinda, it's supposed to be for like, you know, work projects. So I could sneak a funny little microcontroller in there. And just say it's for research if anyone asks. But like, you know, I'd rather not if I can help it. Alright, I wish TI's fancy DSPs didn't cost an arm and a leg. Yeah, absolutely. A lot of picks in here. STM32. Does this thing have USB? Yes, it does. It has USB on the go, which we now know what that means. Okay, ooh, and this is an ARM Cortex M7. Nice, nice. Maybe a little bit extra for what we're going for, but you never know. That text isn't really showing up great. Let me put a slight background behind that. I hit the save button. And we can tell the text to be... No, we can't? Really? Like I said, I could swear there was an option for this. I would like it to be offset from that background a little bit, but I guess there's no helping it. It's in base settings, I think. I'm not seeing it. That might not be a thing for the chat widget. I'm just trying to put a little background behind the text so it's easier to read. That should be more opaque. No, I just wanted that background to, like the background to extend a bit beyond the text, but it's looking like that's not an option, at least not easily. Oh well, I'll work it out, between now and the next stream. Okay, so. Try adjusting size within the layout itself. No, I'm looking in the layout. Nope, it just resizes the text to fit the box. Yeah, again, I'll figure it out later. Up to 35 communication interfaces. Wow, that's a lot of communication interfaces. You know, I feel like they could just, like, generate one datasheet for every microcontroller, you know? Like, I get that they don't want to make someone write the datasheet for everyone when they're so similar, but, like, you could totally just, like, write it in a way that, like, you can run a program and compile the... Like, generate a bunch of different LaTeX files that you can then compile so that you only have information relative to one chip in that chip's manual. Instead of having, like, oh, this is for 4 of these. I have to remember, this is the... H723VET6. H723VE. There. And check the difference between them, which is hopefully in here somewhere. Hopefully. 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 Okay, well, maybe I'll have to look elsewhere. Yeah, I haven't used any of these STM microcontrollers before. But I am happy to learn. Listen, you know, I have a higher opinion of them. I have a neutral opinion of them, which is much higher than my opinion of PICs. Maybe I'm just prejudiced after junior design. Did I miss it? There should be a section on the USB interface somewhere. Art accelerator. I don't think we need this in an audio application, but it's neat. Got 2 embedded op-amps. Neat. Digital camera interface. We don't need this, but it's cool to have it, I guess. Oh, that's nice. It has a LCD controller. All the LCDs I have right now are just like the PCBs that are on, lock them to just using the SPI interface. But you know, I guess I could look into other options. Got a true RNG. I2C interface, USART, low power USART, I2S, serial auto interfaces. There! Section 3.43. Sometimes you just need to find a separate thing. Something, it's not true random. It actually is true random. It specifically is. The thing about microcontrollers is usually they do have a greater ability to get true RNG. Full entropy outputs to the application. It's 32-bit samples. It is composed of a live entropy source analog and an internal conditioning component. It's just manipulating the seed based on player inputs. It really isn't. Oh. RNG True Random Number Generator has been tested using German BSI statistical tests. It's been tested with statistics. The highest of Earthling statistics have been used to verify the randomness of this random number generator. Oh, okay, I believe it now. Yeah, it's simply the truth. It's verified. Alright, Yeah, the thing about these ones is we have to, like, dig deep into the USB audio specs to actually give, like, a controller for that protocol. Whereas this chip will just manage that internally, and we don't have to worry about, like, implementing the audio spec. Blah, 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 blah. Looks good. Let me see if I can find the actual, like... See, sometimes, like, the project data sheet has all you need. Sometimes there's, like, a separate technical reference manual, and the technical reference manual has what you need. And sometimes, as we've learned today, it's, like, a manual that's split up into different sections that are each on their own web pages, and you really can't search for it because searching just brings up one of the sections at random. Can I just get a link to the manufacturer's page on this? Oh, it's a new product. I guess we have to Google it. Right. Oh wow, Edge AI Summit. It's really funny that humans call ChatGPT AI. User manuals, or reference manuals, I think is what we need. Do we have an application at all? This is just like when they said they made hoverboards. Yeah, exactly. Oh, I don't need this. I don't need to measure electrostatic discharge sensitivity, thank you. Timer cookbook. Octospy! Reset search. Is this the same thing? Is it? Oh, there it is. My eyes just wash over it because it doesn't even say USB in this, just says OTG_HS. That's nice that those are the main features, but like I need the details here. Descriptions. And I need more detail here. Dig around on this product page and see if it's around here somewhere. I don't know if this is dual core or simple core. Here, let me close out all of these unrelated ones. I have a nasty habit with these browsers of opening like 2 million tabs. This is a single core. This is a safety manual. I don't need a safety manual. Wait, this is a reference manual, which is, there we go. Look at that page count. That's how you know it's the real one. They call it OTG_HS for some reason. There we go. Okay, let's see. On the go high school. Okay. USB for teens. Well, I'm sure someone has put out a document about this. There's one thing I know about Earthlings, is that they love to put out documents. Nine endpoints. Attach detection protocol. Is there a dedicated core for this? I mean, I think they might, I think I might be using core to refer to not a processing core. Okay. Sounds good to me. Okay. Yeah, this all sounds good. So let me put this on the list as well. Oh, this is very Katamari indeed. Be consistent here. It's 3. Okay. Now this one is more expensive. Although it does have a price dip at 10, so buying 10 of these things would only be what, like $105, which is still quite a lot of money. I don't know. We'll see. We'll see. Maybe if we really like this microcontroller, we can buy a bunch and use them for other projects in the future. All right. That is what this is, right? A Cortex M7, it said? Yeah. Or not this. Give me the actual file. Copy the datasheet link as well. Alright, I think we should take a look a little bit at what the USB audio protocol actually is. Thank you, Hank Muller. In this article, we will look into USB audio, a standard for digital audio used in PCs, smartphones, and tablets, yada yada yada. Host performs an out transfer. It sends a packet of data the device must capture. In the world of USB audio, USB in and out transfers may be used to transport audio samples. An out transfer to send audio data from a PC to a speaker, or as an in transfer to send audio from a microphone to a PC. Like in all these documents, when it says like microphone, our soundboard will like show up as a microphone, basically. Bulk transfers are used to reliably transfer data. They're not considered time critical and are scheduled around the critical transfers. Isochronous transfers are used to transfer data in real time. So I'm guessing audio is probably going to be transferred this way, because you don't necessarily need every packet to be correct, but like if a sample of audio data comes like half a second late, then it's useless. Host allocates a specific amount of bandwidth and regularly performs an in or out transfer on that endpoint. No time to resend data if anything goes wrong. But so if a packet gets lost in transit, there's no coming back from that. But we just miss that packet and have to send the next one. Interrupt transfers are used by the host to regularly poll the device to find out whether something worthwhile has happened. For example, a host may poll an audio device to check whether the mute button has been pressed. The name interrupt transfer is slightly confusing since they do not interrupt anything. Regular polling of data gives the same sort of functionality that a host interrupt would provide. Control transfers are very much like bulk transfers, not time critical, used for operations that are outside the normal data flow. Right, so that's just like giving other like stats or specs of the USB device or stuff that's like controlling other aspects. An explanation on how device capabilities are described is outside the scope of this article. There are predefined classes that enable cross-platform interoperability. Frames, high-speed frames are 125 microseconds. Full speed are 1 millisecond. We probably aren't going to need to implement high speed for this. We can probably just get away with full speed for audio. The human ear can hear what, like 20 kilohertz if we're being generous, and with the so we need to sample at twice that rate, so at least 40 kilohertz. So like it's not gonna be well, 40 kilohertz is actually 40 kilohertz is only 25 microseconds, but also we're probably going to be sending more than one sample in one transfer. I don't know. We'll take a look. 44 kilohertz is a standard sample rate. Yeah, that sounds about right. All audio data is transferred over isochronous transfers. I was right, chat. I was right. Interrupt transfers are used to relay information regarding the availability of audio clocks. Control transfers are used to set volume, request sample rates, etc. Makes sense. Let's just stick that in our little description. And just for reference, chat, I'm going to be keeping notes in this program called Obsidian, which is just a note-taking program. I believe it's open source. It doesn't cost anything unless you want to use their, like, cloud sync functionality. I find it really useful. It's basically just like Markdown. Like, you take notes in Markdown, but it just looks nice, and you can embed images and like just have like a data sheet that you can just have embedded in your documents. And you can do like wiki links between different documents and tag stuff. And yeah, I've been using it a lot lately. It seems like a very useful app to have for what it does. The data requirements of a USB audio system depends on the number of channels, the number of bits to represent each sample, and the sample rate. Typical channel counts are 2, 6, or much higher for studio and DJ use. We're just going to go with 2. Typically, sample size is 24 bits, and those 16 bits is available for legacy audio and 32 bits for high-quality audio. Typical sample rates are 44.1 kilohertz is apparently a standard sample rate, so you're correct, Pancake. Who is this for? I'm going to lie down a bit, cited reason EP. That's extremely reasonable. Who needs 192 kilohertz audio? Like, that's like what? That's like 96 kilohertz, like maximum frequency. 192 kilohertz is like 4 CDs stapled together. Yeah, exactly. Like I don't even have 96 kilohertz of hearing. Why would anyone need this? The latter is used for high quality audio. Too high quality for anyone to hear. Suppose we design a stereo audio speaker with a 96 kHz sample rate and 24-bit samples. 24-bit value is typically padded with a 0 byte. You gotta have $5,000 stereo equipment. Yeah, and like an augmented hearing neural interface, which humans haven't even invented. Have you tried tuning A to 432 Hz? We need to tune A to like 56 kilohertz if we want to use those. This aligns your chakras or something. Okay, yeah, so that's... Okay, let's say we're using, 44.1 kilohertz. That's, 44,100 hertz. Times 2 for stereo. And we'll assume it's also 24-bit values. We'll assume it's up to 32 bits. Okay, so if we're using a full-speed device, that means we have 125 microseconds. 125 microseconds is, it's 10 to the negative 6? Not 10 to the 6. 10 to the negative 6. So then we, oh wait, they've already calculated that, so it's just divide by 8,000. Okay, so we'd need like 45 bytes per transfer. In USB audio, each transfer always carries a whole number of samples. Okay, so they just do it that way. That makes sense. Single isochronous transfer can carry at most 256 samples. Gotcha. Full-speed USB cannot carry more than a single stereo in an out pair at 48 kHz. Well, we don't need more than that. That's perfectly fine for us. Latency is involved. In high-speed USB, this latency is 250 microseconds. We need a 250 microsecond buffer. Extra delay may be incurred in the OS driver and in the codec. Full-speed USB has a much higher intrinsic latency of 2 milliseconds. So we'd actually need to buffer quite a bit of data if we're using full speed instead of high speed. So I don't know. We'll have to look at the complexity difference. If we can do it at high speed, might as well, right? This will only work if the speaker and the host agree on the length of a second. You love to see. And only in hardware engineering do you get sentences like this. Well, hardware engineering and philosophy, I guess. Keyframes, blah 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 blah. In synchronous mode, the length of a second is defined by the host device. Asynchronous mode is the other way around. In adaptive mode, the data flow determines the clock. Adaptive and synchronous mode are not ideal because PCs are notoriously bad at keeping a stable clock. There are often other audio sources involved. Asynchronous mode enables clock sources to be used as the master or a load shitter clock in the device. Typically, either relies on a crystal-based phase-locked loop. Just for reference for the uninitiated, a phase-locked loop, or PLL, is a circuit that basically takes a frequency and multiplies it to a higher frequency. If that makes sense. So if you have a signal that's like, I don't know, 2 kilohertz, you could use a phase-locked loop to turn that into like 200 kilohertz or something along those lines. That's just getting some extra frequency out of it, basically. There are at least 2 separate clocks in the system. The USB clock with a host-driven frequency of 8,000 transfers per second, a sample clock with an externally driven sample rate of 96,000 hertz. Right. The average number of audio samples per frame is slightly more or less than the expected rate. For sleep, I would you like an explanation of the 432 hertz thing? I think it's kind of interesting. Sure, Pancake. Samples. Just requests the current sample rate over an interrupt input. Okay, so it's like they're slightly out of sync, so you also have to, like, tell them, hey, you're giving me slightly too much data, so don't send as much data next time, to sort of keep it going. So the commonly recognized standard for pitch tuning is to assign the 440 hertz as the exact tone that the A note below middle C is. In order to keep a short feedback loop, the trick is not to buffer audio packets and feedback packets unnecessarily. Any additional buffering creates latency in the recording, and this latency makes it more difficult to keep a smooth flow of traffic. The low-level USB stack and the USB audio stack should be tightly integrated without buffering in between. Although this is hard to achieve on an application processor, this is quite easy to achieve if the software is implemented on an embedded processor that has a predictable execution time. Pancake says, so the commonly recognized standard for pitch tuning is to assign 440 Hz as the exact tone that the A note below middle C is. But there's this weird sect of people who claim that detuning your pitches, such as A is 432 Hz, makes sounds better or more binaural or something. There's no scientific basis for this. I don't know, I mean, the places where humans have put their notes are fairly arbitrary. Like, you could change it by a few hertz one way or another. So I don't know, maybe those people just like it better, you know? It's maths you can hear, that's true. I love it when Baba's on a white background. You can pet Baba with the mouse, by the way. In order to keep a short feedback loop, so... Gotten to say my funny audio thing, I sleep now. Alright, good night, Pancake. Have a good rest. Any additional buffering creates a latency in the reporting, and this latency makes it more difficult to keep a smooth flow of traffic. So it's about, like, trying to minimize the extra latency you add, because doing that kind of makes that feedback loop longer and makes it more likely that you'll get, like, a little bit more jitter in the audio. That makes sense. So if that feedback loop takes a really long time, then maybe the audio gets notably desynced from the video. I don't know if that's too important in our application. I mean, it's just a soundboard. The audio is not actually, like, coming from a microphone or anything, so there's not really a lot of synchronization necessary. The above scheme considers just two clock sources. Either the USB device provides the clock or the host provides. Did what pick up on stream? It is impossible for me to know. I did not hear our roommate saying that. I don't know. If our roommate said pig nasty very loudly and it picked up on stream, somebody go clip that. Put that up on YouTube. Other devices that provide the sample rate. USB audio standard allows designers to put a clock selector in the device. This isn't really relevant to us, but it's interesting to look at. so many documents that are not very well described. Oh, this is the adopters agreement. And their license agreements. That's not the device I... Okay, I guess this is what we're looking for. Keep that to the side. Create neatly into the operating system. So the standard makes the device interoperable. OS vendors can supply a single USB audio driver that drives a multitude of devices. Yep, that makes sense. So if we follow the audio class, it'll just work. We don't have to provide our own OS drivers for them. They could... What else is there? Oh, shout out to the chip I already mentioned earlier. Let's see. Synchronous operation. Source and the sync use implicit feedback. Spots are locked to the USB. Sue Puppy, welcome, and welcome Raiders. I'm Digimint. I'm sort of a variety streamer, and today I am doing some hardware design. So I want to give my girlfriend a soundboard, a USB hardware soundboard as a present for the holidays. Yes, welcome in. So yeah, right now we are just looking at various options for microcontrollers. This is the first stream in this series, so we're not very far along in the design process. I haven't worked with USB audio before, so I'm also just looking up some general information about that. But yeah, I hope your stream went well. Oh yes, I can. I've seen a lot of streamers have a bot to automate this, but I do not, so I'll just do it manually. Welcome, welcome. Okay, so yeah, we were looking at... Oh, thank you, I'm glad you enjoy it. Yeah, of course, of course. So we were looking at a, there's sort of like an all-in-one option, which is this USB audio to I2S audio. For those unfamiliar, basically USB is a pretty complicated protocol, so you kind of have to, like, it's a lot of software if you're doing it yourself entirely. But this chip sort of simplifies that process by bridging the USB audio directly to I2S, which is a sort of simpler sound protocol used to communicate between microcontrollers. Oh, thank you for the follow. Let's see. So yeah, if we used this bridge, then my plan would probably be to pair this with the ESP32, which is a relatively simple internet-connected microcontroller. Have to go, sadly, but you have an awesome rest of your stream. Yeah, absolutely. Hey, thank you for dropping in. Alright, so yeah, with this, we could use an ESP32, which is a microcontroller that I have a lot of experience with. It supports the I2S protocol. If I did that, I would probably want it to sort of host its own, host its own web page, so that you could upload a file to the soundboard and do it that way, which would definitely simplify the UI design, because otherwise, I guess I'd have to the simplest way to do it, and probably what we would do to start at least, would be to have it show up as a USB drive. So you plug it in and it shows up as though it's like a USB drive, but you drag an audio file into that drive to put it on the soundboard. Yeah, that would also simplify things because we wouldn't have to implement the USB audio class ourselves, which would be a fairly complicated thing to do anyway. But of course there is extra cost involved there, because this USB audio bridge is $10 just to get on its own, in addition to the cost of the microcontroller. It's definitely a good option. We would have to... I'm kind of leaning towards using just one microcontroller, though. In that case, I've looked at a couple. There is this, there's this 16-bit PIC microcontroller made by Microchip. Personally, I don't know, I don't like PICs that much. I mean, well, I crafted the soundboard myself after I designed it. Yeah, that's the plan. Once we've sort of designed it, I'm going to go through the whole process of selecting components, making a schematic, making the PCB layout. Then I'm going to send off those files to a PCB manufacturer, and when I get those back, I will assemble the finished product. Yeah, that's sort of the goal. We probably aren't going to be able to get that done in December, so it'll be kind of a late holiday present. But yeah, I'm planning on doing all that on stream. Oh, so we can't use Articuno. Did you mean Arduino? I've definitely used Arduino in the past, but I don't know, usually I kind of shy away from doing that. in general, the goal is I want to have, like, I don't know if I'm going to be doing enclosure design because I don't have a 3D printer easily accessible right now. Yeah, Arduino, yeah. Like, I suppose we could, like, get an Arduino and hook it up that way, but also I would have to, like, look at the different Arduino boards and what they support. Because, like, we need something that will communicate over the USB interface. And so, like, I'd have to look up and see if there's an Arduino with USB support. And then there's, like, figuring out libraries and stuff. Yeah, at the moment, the plan is just to, you know, select the microcontroller and lay out our own PCB and such. So, yeah, I was looking into this PIC microcontroller. There's nothing, like, fundamentally wrong with the PIC series of microcontrollers, but I don't know. I've had experiences programming them in the past that are, like, kind of irritating. I prefer not to if I can avoid it. There's also this STM32H723VET6, which is an ARM Cortex-M7, which I haven't actually done ARM programming yet. But, you know, a neutral opinion's better than a negative opinion, so I'm definitely leaning towards this if we go the dedicated microcontroller route. So yeah, I was thinking if we do this, we would need to have, like, we'd have both the audio transfer protocol and then also a different, like, endpoint for transferring the audio files, and maybe we could, like, I don't know, I don't have a lot of experience programming, like, desktop app GUIs, but I know you can do everything in, like, React these days, if you use, like, React Native or something, and I have experience with React, so I could probably throw something together like that. Basically, so you would have a desktop app that you used to set up the soundboard settings, and then that would send the data to the microcontroller, and then set it up, and then once you did that, you only need the app to program it, and then pressing the buttons and playing the sounds happens just over the audio interface. So yeah, that's kind of what I'm leaning towards. Make the desktop app with Scratch. I don't think I can do, I don't think I can build USB drivers in Scratch. Oh, that would be hilarious, though, if you can make it work. But no, I think we'll probably just do it in, like, I don't know, I guess, like, the driver code. I don't know how much driver code is involved in writing stuff like that these days, or if I can just, like, use an interface that already has OS driver code. Like, if I'm writing my own driver code, that'll probably have to be in C, which is no problem. I have lots of experience with C. But ideally, I wouldn't want to make the GUI in C, so, like, somehow have that, like, interfacing with, I don't know, React Native or Python or something like that. You theoretically could, because you can also kind of use Java with Scratch. Oh, that sounds like... That sounds like... that hurts to think about. I don't want to even think about trying to write driver code in Scratch. Okay, so yeah, that's kind of what I would lean towards as far as going for a dedicated microcontroller. That would be $11.50 per microcontroller, but that's also, like, you know, you only need the microcontroller in that case. It's not having to pay for the bridge plus a separate microcontroller. I am going to look around a little bit more to see if there's some other options for us. I know that there are... Some of this family are dual-core. Let's take a look and see. Well, there's no stock on this one, so we can't order that. Let's see. That's another pick. What is this? Marketplace products. Single core, 80 megahertz ROMless. What is this? It has a USB interface. The Hitachi product? Huh. If we use single core, do we need 2 microcontrollers? Nah, we can do all we need with a single core system. We're not doing any, like, complicated DSP or anything. Microcontroller that integrates peripheral functionalities. Blah blah blah. Huh. I think this probably isn't necessary. You see, usually you want to use, like, architectures that are at least, like, kinda common, and this seems like a bit of a weird setup. It's like, if it's too complicated, then you have to, like, use the vendor's tools. And I don't want to use the vendor's tools, because vendor tools are never good. 32-bit RISC-type Super H architecture. So I guess this, like, doesn't have any internal persistent memories. Would we need to get our, like, I'd have to, like, order a separate memory chip and interface that with it. I don't know if I want that. Yeah, usually there's, like, most microcontrollers will at least have some sort of, like, internal, EEPROM.
Ninja 4027 detected.
Oh, thank you for the follow, Ghost Ninja 4027. But yeah, usually you at least have some sort of, like, internal EEPROM that you can use to, like, keep the program on. Really? Oh, this is a mess of pins on this one. I didn't even notice this is a 216 pin package. Jeez. This seems like we do not need this. How much does this thing cost? $38 with a minimum quantity of 8? Okay, no, this is not an option. We're gonna go ahead and skip over that one. It's interesting, but definitely not gonna go with that one. I do not have $300 to drop on this thing. More picks. My goodness. Microchip certainly is making a lot of picks. Who would even use that? I don't know. It might just have, like, a lot of dedicated, like, sort of higher powered DSP functions. Oh, look, it's another one. Oh, this one's 256 pins. Wow, in case the last number wasn't enough pins. Okay, now we're getting into, like, the obsolete products and the out-of-stock stuff. Let's edit our search a little bit. Instead of doing that, we say DSP microcontroller, and then search USB on here. Well, that's certainly an option for how you could do that, DigiKey, yeah. Is there like something I can do to just filter out anything that has USB? No, I don't think so. Okay, so I guess I just select all of these. 46 results. I guess this is probably going to be the same thing. Yeah. Let me just search DSP and see if that helps. I got a whole section here. USB. It's looking like we might get more results here. 671, that's more like it. Okay, so apply those. Oh, and we're getting some TI and Analog Devices chips in there as well, that's good. Oh, there's those TI DSPs. Oh, I do not want a BGA package. I don't want to figure out how to solder a VGA package. Can we get a non-BGA package, please? I would really much rather not. I mean, like, I don't know, if JLC's PCB assembly service, like, can just do this for me, it'll be fine, but I'd rather not have to figure out how this works. Yeah, so this is how we're getting, like, the particularly powerful, like, DSP microcontrollers that are meant for, you know, like, running a bunch of FFTs and stuff. Just doing, like, a bunch of complicated audio processing and stuff. Since we're just gonna be, like, loading and playing back stuff, it shouldn't be, we shouldn't need anything this powerful. We might as well take a look. I have actually done a project using a TI DSP in the past. I don't remember the exact part number of it, but it was like a dual-core TI DSP. I imagine it probably had a USB interface, but I never used it. And that was like... I mean, it was kind of complicated to work with, but that was just because it was like a 2-core processor with a bunch of math instructions. Like, it wasn't that bad. Okay, let's see. Got a floating point DSP core. You do something that powerful for maybe a voice changer, but IDK. Yeah, you could probably make a voice changer with, like, a more powerful DSP microcontroller. I'd have to look into, like, the actual math behind that sort of thing. I don't actually, know a lot about how that works right now. That's definitely something to think about. Not for this project, but in the future. Let's see. Probably a bit more complicated than what we need, but the internal SPI, or no, the internal like SD card interfaces would be nice. We could just store all the audio on an SD card. Oh, here we go. There's an I2S interface. Oh, and 2 buffered I2S interfaces. Nice, that's nice. This seems pretty similar to the one I used. But of course, I don't have the dev board for this thing anymore. Yeah, something to think about if we wanted to go this route. I think this would probably... I need to look into it more, but I think this would probably give us more power than the other options, just in terms of computing power. But probably, like, too much for what we need. So let me put it on the list. So this was based on 674X. Are you planning that the sounds are stored on the board? Yeah, the idea is having like a micro SD card, like sitting there on the, like that you can like plug into the thing, and then the sounds get stored on that micro SD card. Yeah, just to have, make sure we have enough space for everything. I know micro SD cards have like a fairly simple, like, I think it's like an SPI interface. I'd have to look at what the speeds for that are. But I imagine it's probably fast enough for sound in real time. But I could be wrong. We could need to use the faster protocol. There it is. Yeah, seems like a pretty standard USB interface. By the way, if you're wondering what OTG stands for, it stands for on the go. Which, I had to look it up when I first started seeing it coming around. It's like a, it's like a USB protocol where a device can, like, decide whether it is, like, a host or a, peripheral device based on what it's connected to. So, like, if you have, like, a phone or a tablet that can, like, if you connect it to, like, a mouse, it acts like a host. But if you connect it to your computer, it acts like a peripheral. That's what that is. If you see OTG, that just means it's on the go. Oh, good to know, yeah. So this looks like a pretty standard USB interface. So yeah, I think what it's gonna come down to for me is I either want to use this Cortex-M microcontroller or use the USB to I2S bridge along with an ESP32. I think those are kind of my two main options right now. The ESP32 would be handy because we wouldn't have to worry about like a client-side application or anything like that. But also, like, especially for a first prototype, we don't necessarily need to build a whole client application with this. Again, we could just have it, like, identify as a mass storage device, and then you drag an audio file to put it on the drag an audio file, like, into the fake USB drive it gives you to put it on the soundboard or something like that. I know a lot of, like, microcontrollers use that as, like, a basic interface for programming. It's certainly not something you want to do a lot of. Like, the issue with that sort of interface is then there's no debugging capability. And, like, listen, I've done microcontroller work without any actual debugging, and it's not fun. But yeah, I have like an Atmel ICE, which has, I believe it can be used as a debugger for a lot of things, but I will have to look into the debug interface for this. I guess let's take a look at that right now. Pull up this technical reference manual. Let's see. Usually this sort of thing's at the bottom. Debug infrastructure. Debug features can be controlled via a JTAG serial wired debug access port using industry standard debugging tools. Okay, that's a good sign. Excuse me, Lava, I gotta move you over here for a second. I believe the Atmel ICE can act as a, like, normal JTAG debugger. I'll check that. You see, Atmel is the company that Microcontroller used to be. They got bought out a while ago. So now all of the Atmel stuff is listed on Microchip's website. Which sucks, I liked Atmel. If you've ever run with, like, one of the basic Arduino Unos, those are based on the ATmega 328P, which is an Atmel microcontroller. Yeah, it supports JTAG interfaces, so it looks like we're good. Looks like we're good. standard JPEG debug port. I don't think we'll have any particular need for those pins that the debug interface will take up. I guess we'll have to see. I forgot this is the technical reference manual and not the data sheet. See, more complicated, like less complicated microcontrollers only have one data sheet that has all the information. Like the 328p that I just mentioned. It just has one data sheet and that describes everything. But more complicated microcontrollers like this one, usually they have like the basic stuff in a data sheet that you can look at to get the gist of what's going on with this microcontroller, and then a separate technical reference manual. So like if you look at the page count, the data sheet's 235 pages long. The technical reference manual is 3,357 pages long. So it's just like levels of detail basically. Alright, get the pin out. Oh, don't worry, it's normal. Listen. The trick with these data sheets is knowing, like, where to look. And where to look is this table of contents here. So you just, like, look up what specifically you want to know about. Like, most of these pages are probably just, like, row after row after row of individual, like, register descriptions. Just a bit more complicated. I mean, okay, like, the 328p is like a dinky little 8-bit AVR microcontroller, whereas this is like a 32-bit ARM processor. So, like, you know, it's like, it's different levels of complexity, definitely. This one just has, you know, it has a lot of features. It has a bunch of hardware, like synchronization mechanisms and DMA access, which the 328p architecture does not have DMA. And like math accelerators, and like a bunch of ADCs. Oh, and a DAC. Yeah, I guess this is a DSP microcontroller, so it would have a DAC on it. Yeah, it just has a lot of stuff in it, you know? And that stuff gets complicated pretty fast, especially when you have like a cryptographic processor on it. Like, that's going to be complicated to explain. And then like stuff with like camera interfaces and LCD controllers. Like, it's got a lot of things that like make your life easier as a programmer, but it makes the documentation a lot more complicated. Wait, does this thing have an SD card interface? Let's see. I thought I was very crazy when I looked at data sheets of VJTs. Yeah, I mean, microcontrollers are complicated pieces of silicon. Let's see. Oh yeah, it does. Yeah, so we should be fine to just have like a micro SD card and just use this interface. And yeah, like every interface has its like descriptions of this is how the bus works, this is how our hardware exposes the ways of communications and block diagrams and internal signals and timing diagrams, and this is just one peripheral, and we haven't even gotten to the registers yet. And so, like, all of this stuff is managed by control registers, which are like little locations in memory that you write to that have special functions. So you scroll all the way to the bottom here. We will eventually get to, yeah, there we go. And so each one of those little control registers, like you saw all the functionality and configuration that has, each one of those is controlled through these control registers. So there's a lot of them. So that's where a lot of the like page count in this comes from, is just like all of the control registers for all of the individual peripherals and things like that. But yeah, I wonder how long the people took to write the datasheet. Yeah, I mean, you know, the people who design these, they're like big teams. And I imagine there's a lot of just reuse of, you know, if they made a different family of microcontrollers that has basically the same interface for the SD card, then they're going to mostly reuse the same thing. But yeah, it's definitely a lot of effort to write all this documentation. But thank goodness they do it, because it would be impossible to figure any of this out without it. Yeah, I was gonna see... Maybe I'm just used to, those little 8-bit microcontrollers, because I'm looking for a, description of how many hardware breakpoints you have, but maybe we don't need to worry about that. Good old friend Control C, yeah, absolutely. Yeah, all debug port IOs can be reconfigured to other functions. Oh yeah, that's what I was gonna do. I was gonna actually look at how many pins this thing has. I suppose I can just see that here, can't I? Yeah, it's a 100-pin microcontroller. Yeah, it'll definitely be a pain to solder. I'll probably have to just, like, you know, sneak this into the old PCB oven. That's definitely doable. At least it's not a BGA package. Yeah, I think we can definitely work with this. We'd have to think about, so we can probably just like write the firmware in VS Code and figure out what tools we need to do the debugging. I imagine because it's like an ARM Cortex, it's like an ARM core, there should be a lot of support and tooling around to do the like flashing and compiling. Yeah, ARM's got their whole tool chain that we can use for compilation, and I bet VS Code probably has their own stuff. This is some old code. I think we look at the extension list. there's just a lot of extensions for VS Code that should make this a pretty nice debugging experience when we actually get down to the programming part. So yeah, I guess we will have to implement the USB audio device class. So I will need to start looking into that. This is what I was looking into when the all the raiders came in. Let me see. So USB specifications all come in these very long, detailed PDFs that you really have to dig through. I'm pretty sure this is the right PDF. Handling of MIDI data streams over the USB is directly related to audio and is covered in this document. Maybe we're looking for this? Okay, I think this might be what we're looking for. Is this not the same thing as this? In this USB device class definition for audio data format. USB device class definition for audio data formats. Okay, so this is just the same thing. Oh, documentation. Excuse me, Baba, I gotta move you over here for a second. Okay, and I guess we'll have to think about, like, I don't know if I want to think about, like, implementing decoding codecs. I can just, like, do that on the front end. Okay, yes, Ninja, have fun, sleeping. Have fun sleeping. Have a good night. I'll be streaming again tomorrow, but it'll be a very different stream, because I'll be streaming, Sonic Heroes. Most of my streams are not engineering related. I'm just going to be doing this, weekly, usually on Wednesdays. I couldn't make it on Wednesday today, so I'm doing it on Saturday. But thank you, I'm glad you enjoyed. See you soon, Ghost Ninja. Okay, first group, sample by sample basis. Do not preserve the notion of physical channels in transmission. So it looks like we're just looking at type 1 audio. Yeah. Right. And we're looking specifically at type 1 formats. Must be to keep the instantaneous number of samples per frame as close as possible to the average number of samples per frame. Right, so again, it's just we have to pack a bunch of samples into a single USB packet. And because that sort of changes, like the clocks aren't entirely synchronized between the host and the peripheral, there's a whole feedback loop. So ideally we want it to be, we want to like keep everything as in sync as possible. Average number of samples per frame should be calculated as a sliding average over a period of 256 frames. If the sampling rate is constant, the allowable variation on in sub I is limited to one sample. That is delta in sub I equals 1. Right, so everyone, all packets must either contain the average or the average rounded down or the average rounded down plus 1 samples. To limit the needed buffer depths to acceptable limits, the specification limits the cumulative distance plus or minus 1.5 samples. Gotcha. If the sampling rate can be varied to implement pitch control, the allowable pitch shift is 1 kHz per millisecond. We're not doing this. We're not worrying about this. If we want to do like pitch control so you can like do some wacky stuff with the soundboard samples, I don't know, maybe we do that later, but then we'll just resample it. We don't need to worry about that on this side. Audio subframe holds a single audio sample. The specification limits the possible audio subframe sizes to 1, 2, 3, or 4 bytes per subframe. Okay, so that means a maximum of 32-bit samples. Makes sense, makes sense. Audio streaming endpoints must be constructed in such a way that a valid transfer can take place as long as the reported audio subframe size is respected during transmission. If the reported bits per sample do not correspond with the number of significant bits actually used during transfer, the device will either discard trailing significant bits or interpret trailing zeros as significant bits. Right. So we just have to match that to... We have to match the number of bits we send to the number of bits we say we're going to send. Makes sense, makes sense. An audio frame consists of a collection of audio subframes, each containing an audio sample of a different physical audio channel taken at the same moment in time. Yep, that makes sense, that makes sense. An audio stream is a concatenation of potentially very large number of audio frames, ordered according to ascending time. Frames are packetized when transported over USB. USB packets can only contain an integer number of audio frames. Right, so an audio frame is basically one sample for each of our channels. So in this case, an audio frame is 2 samples, one for the left channel, one for the right channel. And let's see. Each packet always starts with the same channel, and the channel order is respected through the entire transmission. If for any reason there are no audio frames available, a transfer delimiter must be sent instead. So my guess is the easiest way to implement that is just having like all zeros when there's no data to send. So just like have it at 0 if there's no data to send. That's my guess at least. We could try the transfer delimiter thing if that sounds weird. But I feel like we shouldn't just be not sending sound, you know? We should just be sending nothing if there's nothing to send. Or, well, we should be sending silence if there's nothing to send, you know? Type 1 format descriptor starts with the usual 3 fields. Format type indicates it's a type 1 descriptor. Number of channels field contains the number of physical channels in the audio stream. Subframe size field indicates how many bytes are used to transport an audio subframe. Bit resolution field indicates how many bits of the total number of available bits in the audio subframe are truly used by the audio function to convey audio information. Okay, so B subframe size indicates how many bytes are in a subframe. The bit resolution indicates how many bits in those bytes are actually useful. Sampling frequency capabilities are reported as well. Okay, so yeah, that makes sense. We can put like, then it's like a variable, and if we want to support multiple sampling rates, we can put all those sampling rates down there. I don't know if we need to worry about that right now, because we're just sending like pretty simple sounds. My plan is that like the client application is going to handle like any resampling that needs to happen, and then probably just store the audio files in like a totally uncompressed and easy to process format. Because like I don't want to try and figure out how to deal with MP3 files in this embedded system. Just have these nice uncompressed like wave files or something that we can easily work with. You can just use PCM format for the audio. The audio data uses a signed 2's complement fixed point format. That makes sense. So fixed point basically means you have like your binary number and the decimal point is always in a certain place. So like if I like, okay, so let's say we're talking about base 10 instead of base 2, right? And we have like, something like that. Fixed point means that like the decimal point is always in the same place. So let's say the decimal point is always after the first. A decimal point is always in like this location, right? And then for this, it turns into so then you don't actually have to store any information about what is and isn't past the decimal, since the decimal always goes here. Floating point's more complicated. it is a protocol where the location of the decimal point is also encoded, basically. Which means that you can store a lot larger range of data in the same amount of space. But it's also just a more complicated format, and you need dedicated hardware to process it and stuff like that. Basically, PCM uses fixed point, which means that, like, the decimal point's always in the same place. And then signed 2's complement just means numbers can be positive and negative. I don't know, I could describe the details of how 2's complement works if people want to hear that. Just let me know in chat, but otherwise, it's suffice it to say, it just allows numbers to be negative. It's like a special data format where, like, it lets you make numbers negative, and it makes it easy to work with negative and positive numbers, but you don't need, like, special math hardware to do it. Data is padded with trailing zeros. The binary point is located to the right of the sign bit. That all values lie within the range of -1 to 1. That makes sense. Basically, yeah, because the values are being stored in binary, when I say decimal points, it's not actually, you know, a decimal point. So when they say binary point, that's just like the binary equivalent.
Thinking where's my trauma? My life's no melodrama. Leave it off the screen, cause it's got no genre. Sometimes I call my mama. Ring. Yeah, she's always my...
Oh, but they also support floating point format in this specification. We're probably just going to use basic PCM. That's kind of the standard, that's why they call it the most commonly used audio format. When we're like transmitting audio.
Tell the clouds that I say
Huh. Logarithmic ending. There's some like special formats here that can be used. Type 2 formats, we don't need to worry about that. USB packets? Audio bit streams are packetized. Each USB packet contains only part of a single encoding. Huh. It's like there's a type 2 way of like not encoding it in the simple way. I don't know if that's particularly useful.
to realize that I'll never be a quarter of the man I could have been when I got older, and all the things I could have done if I was smart.
We don't need to worry about that.
My departure. Fuck, look at the hour.
On the current specification, only MPEG decoding aspects are considered.
It's been 2 days since I've showered. I want to fly away. Far from my mistake.
Like if you had a speaker that could just like handle MP3 and hardware, then you could like do this, and I guess like I don't know if there's any use for that, like because the OS can just decode it and give you PCM data anyway.
Far from my mistake. My baggage.
I don't know if that ever gets used.
So my bed is where I stay.
I certainly don't want to worry about any of this.
Tell the clouds that I say.
Adding new audio data formats to this specification is achieved by proposing a fully documented audio data format for the Audio Device Class Working Group. It is always possible to use vendor-specific definitions if the above procedure is considered unsatisfactory. this is... This document is considered an integral part of the audio device class specification. Huh. Okay, so that's the part, that's just part of the full specification. Like, this is just the tongue, and the whole cave is the whale. Okay. So now that we know about data formats, we can read about the whole situation. The universal serial bus is very well suited for transport of audio, ranging from low-fidelity voice connections to high-quality multi-channel audio streams. The universal serial bus has become a ubiquitous connector on modern PCs and is well understood by most consumers today. With the advent of high-speed USB, consumers can count on this medium to meet all their audio needs today and into the future. It's talking about the synchronizations scheme again. Okay, yeah, so I think we get the big picture. So I'm gonna say, given all this, I think it is feasible to use this microcontroller as sort of our USB audio controller. Again, we are going to need to code like a client-side application for loading the data onto the board. But, you know, we can do that. It'll be an interesting challenge. This is about converters. Interesting. There's just some... This is like control stuff for an audio device. Well, we don't need to get too into the nitty-gritty of USB audio specifications today. We will. Don't worry, chat. We will eventually need to get into the nitty-gritty of USB audio specifications, but we don't need to do that tonight necessarily. Alright, I mean, I guess, do I have KiCad installed? Yes, I do. Give me just one moment to make sure I don't have some sort of personally identifying project open by default. Right. If anyone has like a name for this device, like some sort of snappy, human-friendly name to put on it, I am all ears. KiCad has been run for the first time using the new symbol library table for accessing libraries. Yeah, sure, you can copy the default global symbol library table. Sounds fine to me. Alright. So this is KiCad. This is a sort of all-purpose electronic schematic and PCB layout program. It's free. I believe it's open source as well, but it is definitely free. People who do this sort of work professionally, like, you know, when I'm doing work projects, usually use something called Altium, which is sort of a like an industry version of this. But that's a lot more expensive than free, let me tell you. Yeah, I guess the thing to start with here. Let me see. Give it a moment to load all of its symbol libraries. I want to see what symbols we have here. I don't need the symbol editor. I need to... I gotta get unrusty. There's probably just like a generic USB type A connector. Perfect. Okay, so let's just actually, I guess we'll want this thing to have like a micro A connector, won't we? I don't necessarily know if that's... like, it shouldn't need to be different. Yeah, I don't know why they have a micro B connector separate, but not a micro A connector. Oh well, we'll just use a micro A connector. Okay, so we have our bus voltage and ground. We should, first off, tie the shield to ground. Make a little section out here for power. Actually, I guess this should be a subsheet, shouldn't it? Here, we can... we'll call it, power. Okay, so we'll just put this inside of this, whoop, not that. No, not that. I want to go into the sheet. Which is, how do I get back out? Oh, there we go. Yeah, that's how you do it. Can I just, like, cut that and then paste it in here? Yes, I can. Okay. So we would probably want to a hierarchical pin. Huh, I don't know why that's not working. I guess we have to do that from here. Hierarchical. Yeah, there we go. Okay, what do we want to call this? We want 3.3 volts. We might as well just pass through VBus. And then if we need other voltages, we can handle that. Now, as far as I know, this microcontroller doesn't have the power circuitry in currents to power itself from the bus. Let's see. We'll want to look into USB bus powered devices because there might be some complexity we don't know of. 1.62 volt to 3.6 volt application supply. Okay. I want to look into this filter mathematical accelerator thing. That sounds interesting, actually. FMAC. So this is presumably something that can accelerate running filters. Supports circular buffers on input and output, which allows digital filters to be implemented. So we can do some audio processing on this. If we wanted to do some like weird effects, we can make that happen. That might be neat. We can just have some real-time filtering on the audio. Just have like a switch to do like an echo or a robot or something on the soundboard sounds. I believe this thing only has one USB interface. Ugh. But anyway, that's not what I was going to look for. I wanted to see if this thing had a bus power station. External power supply for IOs. Optional external power supply for battery backup. This power supply must be connected to this when the battery is used. External power supply for the SMPS step-down converter. What is that? Switched mode power supply, power efficient voltage down converter. I suppose we'll have to take a look at that. If this thing has the capability to just do it, then I don't want to worry about buying like an external step down regulator. Backup domain. Well, that's nice. So there's like a separate, like, for really critical stuff, there's like a backup domain so that like you don't totally power off when you have like a battery backup and it lasts longer. The SMPS step-down converter requires an external coil to be connected between the dedicated VLX SMPS pin and via a capacitor to VSS. The SMPS step-down converter can be used in internal supply mode or external supply mode. The internal supply mode is used to directly supply the vCore domain, while the external supply mode is used to generate an intermediate supply level, which can supply the voltage regulator and optionally an external circuitry. Main low power off. Voltage can be scaled by software to different voltage levels that are configured. Yada yada yada. Power supply configuration. Let me... Okay, that's helpful. There's more information on what this thing is. So what I'm trying to figure out is whether I can just power this device directly on the bus and whether it can do the like voltage stepping down on its own. Or if I need to get a separate power regulator IC and connect that. Because the USB bus power is 5 volts. So you get 5 volts off of USB. And this microcontroller runs at 3.3 volts. Plus, if I remember correctly, the 5 volts isn't like super stable. It'll be nice to like regulate it down anyway, because that'll give us a bit more stability. Some peripherals might be used with limited features and performance. Information might actually be on the data sheet instead. Let me see. Power supply management. VDD33 USB allows the support of a VDD supply different from 3.3 volts while powering the USB transceiver with 3.3 volts. VDD has to be above all the other power supplies until it reaches VDD min. So there's a lot of different low power modes on this. Let me tell you, coming from using a lot of like at mega like 8-bit AVR processors, this is incredible. Like there's low power modes on that, but there's not like, you know, voltage scaling. Reset and clock controller. Wait, where? It's not even mentioned. So I think we can't give this thing any more than 3.3 volts. So we are going to need an external regulator, unless I'm seriously misreading this. We very quickly check electrical characteristics. So yeah, we don't actually need to supply this V-core here. Because it can just get supplied. It has its own like internal regulator that we can use. Okay, so that makes sense. So we need a separate we need a separate regulator. A nice little LDO for 99 cents. Let's take a look at this little guy. 80 milliamp linear voltage regulator. Let me check real quick. What are the current requirements of the thing? Let's see. Any information on current? Supply current characteristics. Current consumption measured is measured as described as figure 11. Okay, so if we are VOS 0 is boost frequency. Typical current consumption 215 milliamps. Maximum current consumption could be up to 430 milliamps. We want our regulator to be able to supply as much current as this thing needs. Although there's a limit to how much you can use in USB power. So we might want to consider like power consumption modes. Let me check. Because we don't want to make a port destroyer here. So it looks like when the device first starts up, it needs to be taking... Okay, so this is 100 milliamps at 5 volts. So that's 500 milliwatts of power divided by 3.3. So we can get about 150 milliamps as we're starting up the device. Once we've started it up, we can get up to 500 milliamps, which would be... 750 milliamps at our 3.3 volts. Of course, that's not counting like other sources of current drain, but I think the microcontroller will 100% be the highest draining component. So here, let me real quick make a little page for this thing. Let's make a little section on power. Check the minimum over here. Where was it? It was in here. I already scrolled down. Uh, 1.62 to 3.3 volts. So that's like... We'll call that like 1.7 to 3.3 volts. I guess we'll write it down. 1.62 to 3.6 volts. Current table here. Let me just copy this whole table in here. Why don't I? So the maximum possible current draw from this thing would be 430 milliamps. Actually, I should check. What's the... where is information on what voltage levels that was calculated at? That might be at the top. Power supply is 3 volts unless otherwise specified. Alright, weird voltage to put that at. You think you do like 3.3. But like the maximum possible, and that's if this thing's getting hot. Like we don't, ideally this thing won't be 105 degrees Celsius. Like I don't think we're gonna need to be doing that much audio processing. But like a worst case scenario, absolute worst case scenario, it's looking like 430 milliamps is the biggest one. So again, I just want to like make sure that we're aware of our current requirements and make sure that the stuff we get can support it. So 430 milliamps. But that's also fairly unlikely if we're not using like the power boost. What are the upper and low here? Oh, that's the system clock. Right, that's only if we're doing 550 megahertz in mode 0 with CPU frequency boost. And even the typical's like here. Like, I don't know, it might take some testing if we want to use those modes. But assuming we're using, like, the normal, like, VOS1 mode, then our maximum is, like, 360, and that's, again, only if it gets very, very hot. Where's the debugger section? Okay, let's see, I believe they mentioned it in the power supply management section up here. Yeah, like we're talking like if we're using VOS2, which is sort of the standard area, then like our absolute maximum is going to be 280 milliamps. And again, that's assuming 300 megahertz clock frequency, which we, again, probably don't need. Because we're not doing anything that complicated. Like, I almost want to add the ability to, like, pitch bend and stuff just because, I want to make use of these DSP microcontroller features. Yeah, that would be... that. So the typical value there would even like, I don't know, we would probably want to up negotiate to 500 milliamp USB power anyway. If we have peripherals disabled, I mean, we're doing this on startup, so we can probably assume a fairly low junction temperature anyway. I'd have to take a look at the startup process. I think what we want to do is negotiate for 500 milliamps of bus power as quickly as we can. Let's see. Like I said, we've still got our peripherals disabled. Running in VOS 2 at like a... If we start at like a low power supply VOS 3, then we should be fine. There's no way we're going to get to 125 degrees Celsius before we can negotiate. Like, I think it's reasonable. So we're gonna have to be careful not to draw more than 100 milliamps until we can like start up, connect to the port, and negotiate for 500 milliamps. I think that's probably what we want to do. We want to negotiate for a little bit more, just to make absolutely sure that we have more power than we could possibly draw. If we were making like a full like product to mass manufacture and sell, I'd say we'd want to do more like current testing, if that makes sense, to see what our device profiles like actual maximum current is. But you know, getting like theoretical values should be fine for us right now. So yeah, again, 100 milliamps is 100 milliamps at 5 volts is 151 milliamps at 3.3 volts. Which on our data sheet is something that we can get with peripherals and like VOS3. I mean, it's something we can get from pretty much all of these modes except for like the really high power modes up here with all peripherals enabled at low junction temperatures. But we can't 100% promise that, like, you know, ideally we'd have something to test with and see what it heats up like. But if it happens to like already be hot when it's starting up, like if it resets weirdly, then like we can't guarantee that we'll be getting these values essentially. So ideally, I don't know, we probably don't need to worry about like the junction temperature being this high. Just because it's very unlikely that it ever would get this high. But for safety's sake, having like a starting with a 60 megahertz clock in low power mode is probably best for startup. So starting with a lower frequency clock until we can negotiate up and get, again, the theoretical maximum is 750 milliamps at 3.3 volts, which is enough to power this in all modes. That being said, we will need a regulator that can support this, and this is 80 milliamps, which won't work. Yeah, this is a table. So you've taken a picture of this table with your like Nintendo DS camera. You've taken a picture of this with your Nintendo DSi camera and posted it to this? Wait, this isn't a picture? Or no? Well, this is a PDF, so I can't be sure, but like this definitely isn't text. I don't know why you didn't just like write it out like the other tables in the datasheet. Weird. Current limit is 140 milliamps, which is... Oh wait, no. Trying to figure out where the running is. But yeah, it looks like the current limit on this one's too low for our needs. So we will need to go get another one. Let's see. Current output. Let's see what we can get in the 1 amp range. Why do you need that many pins on a voltage regulator? Doesn't make sense. seems like the ranges they're giving here is a little bit weird. Let's see. Milliamp, 200 milliamp, 350 milliamp. Range one. I guess we would need a... Let's try just filtering this. It's possible our search term filter gave us a weird result. We want the output voltage to be... Three volts, 3 volts, 3 volts, 3 volts? That doesn't seem... That's weird. Not a lot of 3.3 volt options. You think there would be? Oh no, wait, they're down here. They're down here. Yeah. I guess we'll add that in. Never put that there. I guess we can add some of these ones that have multiple options. Yeah, there's all of them. I don't know, we got like 5,000 results. Let's see, voltage, input. Well, that sounds more like it. I guess it was just a weird search result issue. CVN 2 to 5.5 volts. Input voltage version. Yeah, but take 5 volts. Requirement. Yeah, this one's looking pretty good. Only what, 25 cents? 35 cents? Yeah. Well, we can totally make this work. The, typical application. Yeah, nice and simple. But yeah, that looks totally fine. Is this configurable? No, it's fixed voltage. Oh, I guess it's saying that this is a series of fixed ones, but we're only getting the we're only getting the family datasheet because they didn't bother making individual ones for the voltage levels. Alright, so that's looking good. So this is a 1 amp regulator, which means that, like, we can essentially draw as much power as we need to. Well, we can draw as much power as we need to, subject to the limitations of the USB bus-powered, which is fine. Like I said, we can negotiate up to 500 millivolts, which, for this purpose, would be more than enough for all we need. So we want to use, I never remember the order of things in markdown links. It's square brackets, CLV 1117, LV 33 DCYR, and then there's the link, and perfect. Okay, so this chip will take the 5 volt USB bus voltage and just convert it down to 3.3 volts for us. Because we don't really need the 5 volts for anything. I mean, the USB interface, I believe, has its own power supply for that. But we can just connect that directly to the bus. But the rest of the microcontroller is going to operate at 3.3 volts. So, here's what we can do. Click this down. Oops, wrong button. And the part number here is... I think I got it. Oh yeah. Perfect. Put that right there. Will be... You wanna annotate this stuff. Where did my line go? Okay. Yeah, you want to annotate this stuff. We can import those hierarchical pins. Hello? No way, that's... I don't know what's going on there. Do I have to, like, have it connected to something? I bet that's what we have to do. No? Water. I guess we look it up. not the best documentation here. What's going on? Do I need to like do this from here? Let's hierarchical label that works. Okay, so wait, that showed a different thing. I don't know why I can't. Oh, wait. Oh, okay. Yeah. Or no, label will be seen as a hierarchical pin in the sheet. Where? It's like not saved. Oh, no, wait, that's... What? Oh, did I... Oh, are those placed as the wrong thing? Is that what's happening? Figure out how to do this.
What happens when life breaks down? God himself puts his arms around you.
We should be able to place these. Hierarchical pin sheet. What's going on here? Do I need to like label this net? Okay, if we label this net, can we do that? No? This is extremely bizarre. I don't know why that's not working. We can do this. Is it like... Is it backwards? Do I have to do this button? Let me... And if I go up a level in the hierarchy, that's not what I wanted. Phase. Huh? Change. Okay, so yeah, okay. It's the other way around. Okay, sorry for the confusion, chat. So if we go import sheet pins... Okay, so yeah. Hierarchical pin is in the sheet. Hierarchical label is like in the sub-circuit. So I'm glad I'm safe now. You can calm down. But let's like... You gotta make your circuits aesthetic, chat. That's the important thing to know. Anyone can make a circuit, but only a professional engineer can make a pretty looking circuit. Take notes. Net named grounds. Place that there. We want to leave room for the input and output capacitors. Okay, and the capacitor. Typical application. 1 microfarad ceramic capacitors are required at the outputs. Alright. Yes. There we go. This. On this actually. use X5R and X7R type ceramic capacitor. $0.10 for a capacitor. That's a lot for a capacitor. I guess that's why they tell you to use these special ones. Now, usually 10 cents isn't that much, but like for a capacitor, that's a lot. Just search up like capacitor and pull up just generic chip capacitors. Oh, never mind. Oh, it's just because I'm looking at the quantity for one. Oh, silly me. Okay, so with this X5R... Yeah, see, if we're buying 10... we can literally get 10 for the same price as one. They extremely don't want you ordering small quantities of these. For reference, $10.45 gets us 5,000 of these. $20 gives us a whole freaking reel. Let me put that in there just as a note. Although an input capacitor is not required for stability, a good analog design practice is to connect a 0.1 microfarad to 1.0 microfarad low ESR capacitor across the in and ground pins of the regulator. Seems reasonable. That goes to the output. Huh. Line the board with separate ground planes for VIN and VOUTs, with the ground plane connected only at the ground pin of the device. And we're not doing any like analog signal processing on this thing, so it's not like it's super duper important to be getting the maximum performance, but this stuff is good to know. Like, let's put this at 1 microfarad. I guess we should put the USB in a separate circuit from this, shouldn't we? We just have, yeah. We put a separate sheet, how you do it. Viva shouldn't be an output of this. Please. So we want this to output the bus and USB ground. The B in bus here is not capitalized, and this needs to be an output. I guess it's weird to, because it's this is like a passive. I think that would make more sense. Alright, and then we have this as, again, a passive. We have our regular grounds. And of course we just connect these up. But VBus is an input to this one, and then we paste this here. This provides VBus. And then we need this is USB D plus. USB DM. Outputs. I guess they're like. Let me check. Okay, so yeah, these are both, I guess these are both IO. I don't know, it's here. There we go. Stick a pin here. And that's our USB grounds. This one's actually pretty simple, although I believe all right. Some connector stuff. I'm just checking around to see if I can get some good answers for what the recommended layout of this is. Because again, I've never really worked with USB before. Like it's the exact details aren't that important for our application. I want to make sure we're more or less doing it right though. Let me see, there might be something on our data sheet. Let's see, there might be more detailed information in this document. Oh, that wasn't even the same document. And our USB module. Our USB module is right there. Where are the layout guidelines? Datasheet should have guidelines on how to do this somewhere in here. Implementation. So it looks like it's not suggesting any like extra stuff on this line. Oh yeah, there we go. To build a bus-powered device implementation in case of the B-device or peripheral-only configuration, an external regulator has to be added that generates the necessary power supply from V-bus. That makes sense. Yeah, there it is. So I'm glad we looked that up. There's 5 volts to VDD voltage regulator right there. Use a regulator to build the bus power device. What's going on there? Yes, this is saying, like... What is this component? Hold on. See what it's suggesting we use. This is just a power switch. Huh. Does it do any regulation? I don't think so. I think it's just a switch. So what is it trying to tell us to do here? I'm not sure why the switch is necessary. I wonder if this is just saying, like, well, this is saying peripheral only connection. Yeah, I'm not sure what's going on with this switch. Like, our VDD is only 3.3 volts, so we shouldn't be connecting that to 5 volts, definitely. That is strange. Yeah, I'm not sure. But it does seem to be saying that, oh yeah, there we go. See, that's... Okay, so this is just saying that, like, you can... Huh. Strange. Yeah, I don't know why it's saying to put VDD here, because VDD can't be 5 volts. Very strange. I don't know, maybe that was just a mistake in the datasheet. So yeah, it's looking like they're not mentioning anything about, like, supporting circuitry. Okay, so that just means, like, adding the proper resistance at the end. Let me see. Negotiation protocol. Search for impedance. See if it's mentioned anywhere here. Because what I really don't want to do is to not include that resistor and need to. Where is this? Section 64. 4. Section 59. USB is mentioned 3.43. Oh, welcome, Orange Peel. Internal input impedance. They're all DAC characteristics. Oh, there. Okay. Yeah, there's no mention of impedance matching here. So I guess that's just done internally in the USB PHY, so we don't have to worry about it. Alright, well, if we need to change that, we can always just get out a scalpel and make some trace modifications on the PCB afterward. Make sure this is connected properly. Okay, so I guess the only place these are connected should be the ground pin here. And we want this to be B bus coming in from the USB. That's not correct. Enter this. There we go. So that's the voltage regulation done. And I guess we technically don't need VUSB grounds to come in here. Although we should put that in here, actually. That one is a passive. I'm going to move this over by one more. Okay, perfect. If I could choose between Altium and KiCad, which would I choose? I mean, I feel like Altium is nicer to use. Like, having used both, I can see why Altium is an industry standard in a way that KiCad isn't. Like, I really appreciate KiCad for being an open source option, but Altium definitely has, like, features and functionality that KiCad doesn't. Like, especially in the realm of, like, DRC and, like, auto routing, there's really no competition. I still really appreciate KiCad for what it does. But Altium is definitely the more feature-rich of the two. Okay. This is going to be the MCU. It should be MCU interface. Let's see if KiCad has it in the symbol libraries. Also, Altium has some nice features for like auto importing symbols and models and such, which KiCad does not. Okay, let's see if KiCad has this part. No, it does not. Okay, that's okay. We have... They have... Oh, they don't. Okay, so we'll have to make our own for this, but it shouldn't be too hard. It'll be a little bit irritating. We just need to find the pinout for this. Okay, and this one is the LQFP. Okay, I'm gonna put this up on my other monitor. I have a blown up version. We're gonna have to make a symbol library here. Okay, we do need to make another library. New library. We'll just make this project-specific library here. Okay, and this will be, there. Okay. Is there like a... Looking like there isn't. Is there really no... Wonder if we can, No. Okay. This is gonna be irritating when we have to make the PCB symbol for, certainly. Okay, well, time to manually place 100 pins. I'm sure this is going to be riveting Twitch content. Get your fingers on the clip button, everyone. This is, top tier content. Switch over to the data entry category. Well, I'm glad you like the background track. Yeah, what's been playing is just Monster Cat's default chill playlists. Okay, guess let's go a port at a time. Start with port A. PA0. Bidirectional, this is pin number 22. How many pins do they have? 1, 2, 3. 4, 5, 6, 7. 8, 9, 10, 11, 12, 13, 14, 15. Okay, so 16 each. I should make sure that I have these entered right. The A1 is pin 23. PA2 is pin 24. And so on. Up to pin 28 for PA4. Nice, 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 nice. Just do it real quick, a slightly more in-depth check to make sure there aren't any CAD models for this around, because again, there are 100 pins on this thing, and I don't want to have to define all those. STM32H723VET6. Oh, thank goodness someone has done this. We have KiCad V5. I guess I should check the newest version. Hold on. I'm like a version behind on KiCad. What is the current newest version? Version 7? Okay, I'm a little bit behind. Hold on, let me close this. Don't save that. Oh, gigabyte download. Okay, while we're waiting. Oh, I gotta log in. One moment. I believe I do have an account here. Oh, I have an account, but my username in my password manager is just NA. Let me make a new account, I guess. Okay, first name, Digi, last name, Mint. Company name, no. Industry. Other. Preferred CAD tool, KiCad. Country. Well, the right answer isn't on this list. But such is to be expected. And there's a password. Well, I love to agree to terms and conditions. I love to select all squares containing motorcycles. What are you talking about? I just registered. Okay, there we go. There we go. All right. Ask for the KiCad models. Guess we'll download the 3D CAD models as well. Oh, 94 at Mouser. Hold on. Oh, yeah, $7.94 if you buy 500 of the darn things. Oh, import guides.html. Okay, so it imports itself as a library. Let me go ahead and install the new version of KiCad. Ah, there we go. So that should open the... No, this opens the old version, I guess. We gotta go into program files. Okay. Okay. Fancy new interface. Let me see if our microcontroller has an entry in the new symbol library. That's a no. Yeah, go ahead. Is this saying they don't have one? STM32H7. Oh, wait, there's no symbols in here? What's happening here? Seems to be having some trouble here. Huh. Strange. Oh, is it because... Did I have that thing still in the search? Oh, I did. Okay, so it's telling me that this isn't in here. Or it's not just a... M32 H723 VET6 H723 VET6 VETX. So I guess this is just a generic for that whole family. They have the same input interfaces. That'll speed up things considerably. Okay. Yeah, we'll have to allocate things as we start deciding on functionalities and input mappings and things like that. But for right now, it is getting pretty late. So I am thinking that we should probably call it for tonight. I think we made some good progress. We settled on a microcontroller to use, and sort of set out a little plan and got some basic part selections and things like that, and started the schematic layout. So yeah. I hope everyone enjoyed the stream. If you enjoyed the stream and you haven't yet, don't forget to drop a follow so that you will get notified next time I go live. I'm planning on streaming Sonic Heroes tomorrow at 2 p.m. Central Time. So yeah, we will be we might even finish the game tomorrow. I think I probably am just gonna go late until we finish, because all we have left is Team Chaotix and then the final bit. So yeah. Then after Sonic Heroes, I guess we'll have to move on to a different game. We'll have to think about that at the end of the stream. So yeah, be sure to catch that tomorrow. Other than that, let's see, I've got Minecraft with Pancake again next Tuesday. And we probably, I think I might just do this on Saturdays. I'm thinking, so Minecraft on Tuesdays, probably more Spark 3 runs on Thursdays, and this on Saturdays. And then Sonic on Sundays, of course. So yeah, we have a Discord server. If you haven't joined it, !Discord in chat. You can go there if you'd like to chat with folks and get an alternate way of getting notifications for when I go live, because I know Twitch sometimes is weird about sending notifications. But yeah, I think that's it. Once again, I hope you enjoyed the stream, and I hope you have a wonderful evening. I'll see you tomorrow. Have a nice day, everyone. Bye. Wait, I can wave bye. 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 Okay. See ya.